All right, so bounded by the x-axis, x equals 1, which is right there, x equals 5, which is right there. So that's a pretty obvious one. And then the strip idea, right? So again, and the reason I want to emphasize this is because it's so important for what we're doing today. So what we're doing here is we're wanting to add up the area of all these strips, right? And the area of a strip is the height times the width. The height of this strip, again, I can't emphasize this enough, the height of this strip is this y value. What is this y value? Well, it's right there, 1 over x squared. So this strip, if I call it S, is 1 over x squared minus 0. This y value minus this y value. Now, I realize this is just our basic area under a curve because it's the x-axis, but it's not always going to be that, so it's very important we understand. So we're adding up all these strips here from 1 to 5, and the reason it's 1 over x dx, 1 over x squared dx, because this is the height of the strip, and this is the width of the strip. Height times width is area. The integral adds up the area of all those strips, so we get area. Okay? Important to understand. Okay, what about 15? What did you get for the answer on 15? 2. What is your integral on 2? X cubed. How'd you get x cubed plus 1?
Or I guess it was pretty sure x cubed minus 2x plus 1 plus 2x.
Because it was f minus g. Now, you really need to have sketches of these, okay? That's kind of what I was looking at there for you guys. You need to have, it says right here, and on our quiz, when we do this, you are going to have to sketch the region, just like it says, sketch the region bounded and find the area. So you're going to have a sketch, you're going to have an integral, you're going to have an answer. Now, in this particular case, in 15, the cubic here goes up, comes down, I think it, oh no, that's, yeah, dips just a little below and goes like that, right? And then the line, negative 2x, that comes kind of through here like that. And then it says, and then also intersected by x equals 1. And x equals 1 comes right about here. Okay? So it's this region right in here that we're finding. Okay? Well, what are we going to add up? We're going to add up these strips, the top of the curve to the bottom of the curve, like that. Okay? So this y value is the cubic. So it's going to be x cubed minus 2x plus 1 minus this y value, which is negative 2x. And so it ends up being that, and then the 2x's cancel out. And so you end up, as you said, x cubed plus 1. Now you also have to find this intersection point, right? You have to find where they intersect, which is at negative 1. And then, of course, this over here was a line y equals 1. So the integral is negative 1 to 1. Okay? So, finding this region, setting up this integral, been a few days since we had to do any of those. Okay, now, next page. We had, what, 20? We had on this one, 21 and 23. Okay. So, Will, you didn't have these, right? Okay, so you tell me, how do I graph f of y equals y squared? What is f of y? That's just x. So we're graphing x equals y squared. Any idea what that looks like without going to the calculator? Sideways parabola. Okay, a normal, basic sideways parabola, just like y equals x squared is your. So it's that. But it's both the top and the bottom half. That's the difference. It'd be the same as y equals plus or minus square root of x. Now, we can put on our quiz, our next quiz, you can use your calculator, okay, to graph that. You can use that relation mode. But on the packets, on the final, it could be a no calculator, especially one as simple as this. Okay, what's this one? G of y equals y plus 2. That's x equals y plus 2. Well, to graph it, I would say you would solve for y probably. Right? So slope 1, y-intercept of -2. So down here, -2, and it's going to go up like so, slope of 1. Okay, so somewhere this is going to cross like that, and we're going to have this region. Well, what kind of a strip would work best here? Horizontal strips. Now, we're going to get into that today with our volumes. We're going to talk about horizontal strips, but horizontal strips would be the best. Okay, horizontal strip right here, because those horizontal strips go all the way from here up to here, but we got to find where those intersect. Okay, well, what is this point right down here? I think it's 1, -1, isn't it? I mean, I think that's a point 1, -1. If you put a -1 in for y, you put a -1 in for y, you're going to get 1 for x. You put a -1 in for y on this one, okay? And then where's this intersection? I think it's probably 4, 2, right? 2 squared is 4, and here if you put a 2 in for y, 2 plus 2 is 4, so 4, 2. So these strips are going to go from where to where? -1 to 2. So this integral is going to go -1 to 2, and it's going to be this x-coordinate. What is this x-coordinate? What's the x-coordinate of the line? Emily, what's the x-coordinate of this line? That is the y plus 2, right? Very good. That's what I told you guys I wanted you to say when I asked that, right? What is the x-coordinate of this line? Right there. It's y plus 2. Okay? So y plus 2 minus, Will, what's the x-coordinate of this parabola?
Y squared.
Y squared. And then don't forget the dy. So right minus left gives you the length of the strip, dy is the width of the strip, those multiply to give you area of the strip, the integral adds up the area. Okay? And then what was the answer in 21? 9/2. Okay? 23. Max, what does the graph of this look like?
The same side of the graph that shifted.
No? Not shifted up one.
Shifted back. Or right.
Shifted right one. Okay? So it's like that. It'd be just like if you shifted it up with the other one, but it's, okay? So that's shifted. I think you don't have that right. Okay? And then what is this? Skylar, what's g of y equals 0? Which one? So let me ask it this way. What's g of y? What's another name for g of y? What's another name for g of x? Or f of x? That's the y. So what's g of y? X, right? G of y is the same as x. So that's x equals 0. Which axis is x equals 0? The y-axis. So g of y equals 0 is the x-axis. So this is what I'm talking about. We won't be able to do any volume problems or any area problems if we don't know what these graphs are, right? If we can't graph these graphs, I mean, we will not be able to get these regions. So that's why that's why we need to know this. And if you had questions, I guess what bothered me, we didn't have a chance, or we didn't take the time the other day to go over these, but because we were in the package, we were doing some stuff, but some of you guys didn't have them done, and you never came in and asked, right? You never said, hey, I couldn't get 21. I wasn't sure how to graph 23. I mean, come on. Year's not over yet. Y equals -1. Okay, comes through like that. All right, and y equals 2 would be up here farther. Okay. So we're talking about this region right in here. Okay, horizontal strip would be best. like so. So this x coordinate is y squared plus 1 minus this x coordinate, which is 0, and then the hardest part of this one is just finding where they intersect. Okay, so well, it's not hard. Where does y equal -1? Y equals -1, we just put it into here. 1 plus 1 is 2. So this would be 2, -1. This one was y equals 2, so we know the y is 2. Put a 2 in here, 2 squared is 4, plus 1 is 5, so that's 5. But it doesn't really matter. We're just going from -1 up to 2, so really we only needed the y value, so it doesn't really matter. -1 to 2. And the answer on this one was what? 6. Okay? All right. So let's get looking at what we did yesterday. Okay, so just a second here. All right. All right, here's the problems we had. So just to summarize what we talked about yesterday. So think of this like the lemon, but what we were saying was we were going to take some two-dimensional region like this pink region, and we were going to revolve this around an axis. In this case, we're revolving around the x-axis. So there would be like this reflected area over here, and it's actually a lot like this. So the actual three-dimensional object we're looking at is something like this. So we're creating a three-dimensional solid, and we want to find the volume of that. Well, we're going to use the integral to do what? How's the integral going to help us do the volume of that? Add up all the slice volumes, right? Add up all the slices. Circles, now technically they're not circles, but they're cylinders, right? They have a teeny bit of thickness, which we call what in an integral? Dx, right? So it's basically going to be the area of the slice. It's going to be the area of the slice, area of the circle, times the dx thickness gives us volume of the slice. So we're going to have volume of the circles. That sounds weird to say volume of a circle, but that's what we're doing really. It's a cylinder, but we'll just say volume of each slice, and the integral then is going to add it up very good. So you understand that concept. And so here's what the integral does. It's going to add up the volume of all those. That should give us the volume of the whole thing. Now, you don't have to be able to think of that three-dimensional shape. You don't have to draw the three-dimensional shape, but you got to understand that this strip right here represents what in a slice? It is the radius of the slice. This strip right here, that's where this top minus bottom that we just got done doing, this strip right here is the radius of the slice. And so if we want to do the area of a circle, it's pi r squared. So we're going to take pi times this strip squared. Pi times the strip squared is what we're going to put in the integral. Okay? Because you'll have pi times the strip squared times the dx. That'll give you the volume of the strip. That's the bottom line. Now, what it looked like yesterday with this was something like that. We actually did slices, and so if we had all of them, if we had, if we showed all of the slices like yesterday, we had all of these Guess I'll quit trying to do that. Doesn't matter. Okay. Maybe I can't do that. Oh, that's what I have to do. No. Okay. So that's what we did with our lemon. We did those slices. Now we did an average radius thing, but if we would have just taken one side of each of the slice, say the right edge, 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 and have these cylinders, it would not be an actual, but we fudged it a little bit. We did the average radius on each side, kind of like a trapezoid kind of a thing. But anyway, that was the idea. We don't have to worry about that as long as we understand that what we're doing is this right here, okay? That we are finding those areas. So this is when we revolve a solid around an axis. So for your notes, this would be a good thing to put down. So how do we find the volume of a solid by slicing? It is this formula right here. Now the key for us is going to be identifying what the slices are. Identifying what the slices are. But this is finding the volume of a solid by slicing. Now, sometimes it's called, instead of slice, this is sometimes called cross-section. It's the same thing. Okay? So sometimes they'll say the area of a cross-section, or it'll say the cross-sections of the solid are squares or semicircles or something like that. Okay, but then when they say cross-section, they mean slice. Same thing. All right, and the dx, of course, is the thickness. So when you take area times a thickness, you get volume. Area times the thickness, you get volume. And I probably should put V equals here. V equals that. Okay? Very simple formula. So all you need to do is write the area of the slice in terms of the functions that are given. And then the key to that is going to be the strip. If it's a circle slice, the area is pi r squared. You got to find what r is. R is the strip a lot of the time. Okay? R is the strip. So whatever the strip is, and how do we get the strip? How do we get the strip? Top minus bottom, or right minus left. Right? We get the strip by top minus bottom or right minus left. And once we have the strip, we figure out what part of the slice it is. We write our equation, we put it into the integral, and we got it. Okay? All right. So, what are some common types of slices? Well, the one we've done so far is a circle, or sometimes called a disc, and the area of that is pi r squared. And so, usually that looks like something like this. Right? Circular type slices. Okay, or they could be horizontal. That's not very good pictures, but whatever. Right? So we could have slices that are circular type slices. Okay, and we're going to add to this list today. All right, so let's look at our homework problems. Okay, so this was number 1. I think. Right? So, we're revolving around here. Now, did they draw strips in there for you? Or a strip? Yeah, we only need one strip, but there'd be, the integral's going to add up all the strips. So they already drew it in there for you, didn't they? But it actually would be easy to do it either way, right? You could do horizontal or vertical strips. If we have a choice, I think we usually do vertical strips. Okay? So, we want to do the volume, not area. We're not doing the area of this thing. We're doing the volume of this. Now, what would this create when you revolve this region around the x-axis? What kind of shape? Makes a cone, doesn't it? Makes a cone. Because you're going to revolve this region. It's going to come down to here, and you're going to have this kind of this circular thing, whatever, and you're going to end up with a cone. It doesn't matter that you know that that's going to be a cone. And actually a cone is easy. A cone is 1/3 pi r cubed h, or pi r squared h. We've already done that. Well, this would be a cone that has a height of 1, and it's got a radius of, what's this point up here? Is that 0, 1? And this point is, oh wait. Yeah, and this is 1, 0, right? So this is going to have a radius of 1. It's going to be a cone with a radius of 1. And it's going to be a height of 1. So this is going to be 1/3 pi. This, right? We know that. It's a geometric shape. We know this should be 1/3 pi when we get done, okay? But it doesn't matter, okay? And we don't have to draw any of that red stuff. The only red thing we need to draw is this strip, okay? Now, I'm going to, so and it would be good to think of your slice. What is your slice here? What shape is that? It's a circle, right? It's a circle. I mean, think of it this way, right? You got that strip sitting on the x-axis, just like this. It's revolving around. What does it create? I mean, just take when you're sitting here on the test next week or whenever we do this, grab your pencil, you're sitting there, and I watch you do this, and I know what you're thinking, right? I mean, that's, right? This is what's happening. This strip is revolving around the x-axis. Look what that marker is creating. It's creating a circle. And this marker is the radius. This is the radius of that. So you don't have to draw it in there, but you got to picture it happening. So I would write R equals, I would get in a habit here, and you could write R of X if you want, but R equals the top minus the bottom. Well, that would be negative X plus 1 minus 0, right? That strip is the radius of this circle, and what did we just learn back here? We learned that to do the integral, we need the integral of the area of the slice. Well, the area of the slice is pi r squared, so we need pi times our radius squared times our thickness, and then the strips fill the space from what to what? 0 to 1. Now, a lot of times you see the pi out in front. That's fine. You put the pi out in front of these. That's okay. Okay. But pi r squared, and there's your thickness. That gives you volume. The integral adds it up. Questions about that? Okay. Some of you had questions on the last ones. I don't think they're any harder than these if you really understand what's happening. So, but that's okay. Let's get this clarified a little bit here. Okay, here's your strip. This is going to create some kind of round bowl-shaped kind of thing like so, right? And these are going to be circular slices. We don't have to draw it. Doesn't matter, but you got to understand when you revolve, anytime you revolve something, it's going to create a circle, right? It's going to create a circle. So this strip is going to be our radius. So top y value is 4 minus x squared. Bottom y value is 0. And so we're going to have pi, put it on the outside, r squared dx from, and the strips are going to go from 0 to 2. Okay, what's the answer on that? 2 what? Oh yeah, 256. I like 256 pi over 15. There's no reason. If the calculator gives you 256 pi over 15, put 256 pi over 15. Right? There's no reason to go to a decimal. But you can. Just make sure it's 3 decimal places. Okay, so we had pi thirds and we had 256 pi over 15. Okay, next one, number 4. Again, revolving around the x-axis. So the idea was to start with real simple ones, and we're going to get all kinds of weird things going on today. But here's y equals x squared. We're going to revolve this around, what is some kind of bugle thing or something? Wouldn't it? I mean, megaphone or something like that, right? Isn't that what that's going to create? Right? Your slices look like that, right? But I don't care if you don't have to draw that part. But what you got to know is of this circle, this is your radius. So your radius is going to be your top y value minus your bottom y value. Okay, so your integral is going to be pi x squared squared dx, and these strips are going to go from 0 to what is this? 1? 0 to 1. Pi fifths. Pi fifths. Aren't these easy? Compare those to optimization problems. All right. Number 9. Okay, now we start changing it up a little bit. Now we're going to revolve around the y-axis. Is this, Emily, this is where you were questioning, right? 9 and 10, is that y because of the y-axis kind of thing? Yeah. Okay, So if we revolve this region around the y-axis, then what are we going to have? Aren't we going to have just that kind of a shape, right? Where your slice is going to be. And it will usually say in the directions that the slices are taken. What did it say here? Did it say, oh, that's wrong. What did it say here? Find the volume of the solid formed by revolving the given region around the y-axis. Now, they already had this, but usually what it'll say is the slices taken perpendicular to or whatever. Well, that's not even true. A lot of times they just tell you where it's revolved around, and when it's revolved around that, your slices are automatically perpendicular to that axis. So that's actually an automatic. So it actually, I take that back. So that means we're going to have horizontal slices, right? Here's going to be a slice right here. Right? There are going to be a bunch of those slices, but it's going to be a circular slice at your radius. What is the radius? What is the radius? It's the length of that strip. Jesse, how do we find length of a strip? Top minus bottom or right minus left. In this case, it's right minus left. So this radius is this strip. What is this x-coordinate? X equals plus or minus square root of y. So like the question Emily asked you earlier, right? What is this x-coordinate? It is x equals, right? And which one is it? The positive one. This is positive square root of y. This is negative square root of y. So this x-coordinate over here is square root of y. Minus this x-coordinate. 0. So my volume is pi times my radius squared. And the strips fill the space from 0 to 4. Now again, this is an old book, and the idea was that you would not be able to do these by hand with a calculator. You would have to do it. Oops, that would just be y, right? This would be a real easy one to do. 1/2 y squared, integral from 0 to 4. Put in a 4, 16 times a half is 8. Put in a 0, you get 8. So what is it, 8 pi? Was that the answer? 11/9? 8 pi, right? I mean, we could have done that with. So if we said, you know, use the fundamental theorem. So if we said, you know, no calculator, we said use the fundamental theorem to find the volume, that just means set up your integral and then do it. Remember, anytime you have a definite integral, there's 3 different ways you can do a definite integral. It can be just geometry, which is not going to happen here. It can be by the fundamental theorem, right, where we have to do the antiderivative and right minus, you know, big F A B minus big F A, or an approximation technique, or I guess calculator, right? I guess you could throw calculator in there, just let the calculator do it, right? It's going to do one of those techniques, either approximate or whatever, okay? But don't forget, you know, I might have you that on the quiz. My plan is let you just use calculator. Just want you to make sure you get them set up. Okay, now what kind of a picture is this? Right away, as soon as you see that. It's a circle, right? That's a circle, radius of 4. So if we revolve this region over to here, right, what are we going to create? A semi-sphere, right? It's going to be half a sphere. Now the formula for volume of a sphere is 4/3 pi r cubed. This is going to be a 4 cubed, that's 64. 64 times 4 is what? 256 pi over 3. Did I do that right? But it's only half of that, so it's 128 pi over 3. Is that the answer to this one? 128 pi over 3, right? That's geometry. That's going to make a sphere, so we should know that. But let's do it with our calculus. So we're going to revolve around the y-axis, so our strip's going to be here, right? Our slices are going to be this way. Now, we could, right? Our slices are going to be that direction. All right, so our strip is our radius of our slice. So our radius is, what's this x-coordinate right here? You can just interchange those? Sure you can, because if you square both sides, right, just make sure we understand what we're doing here. If we square both sides, we get this. If we add x squared over to here, subtract the y squared over here, and then we square root both sides, we get 16 minus y squared. So that's what it ends up being. Now, it's plus or minus. This side's the plus, this side's the minus. So it turns out that this x-coordinate is square root of 16 minus y squared, minus this x-coordinate, which is 0. Okay, so we get pi times our radius squared dy, and our strips fill the space from 0 to 4. And we should get 128 pi over 0. Okay? All right. Well, it's time for us to do something a little different here. It's time for us to take this region right here, okay? So in your notes here, wherever, on your homework page, I don't care, I want you to draw that region right there. Find the volume of the region bounded by y equals square root of x, y equals 0, x equals 4, when that region is revolved about the line y equals -2. So first let's get the region drawn. Get your calculators out here because we're going to be doing some graphing and some setting up some volumes. Shade in your region. Shade in the region that's being revolved. All right, now, this should be the region that you shaded, right? You do not shade down below that. Here's where we're going to revolve it. This is called the axis of revolution. Okay, where do I draw my strip? Where have we normally drawn our strip? Right in here, right? Well, I got news for you. That strip ain't going to mean anything to us this time. Now, let's take a look at what this picture actually looks like. Okay? Okay, now I've actually put it down here. Is it y equals -2? Yeah. And then where were we going? We were bound over here. Oops. And 4. Right? So let me go ahead and move. So here's actually the picture we're looking at, right? We're looking at this problem right here. Okay? Now, can you picture that solid? I think I showed it to you yesterday. Now remember, we're talking about the volume of the solid. This is like made of plastic or metal or something like that. You know, when you're in 8th grade, you learn about volume. You talk about volume, or middle school, whatever. You're really talking about empty space, aren't you? Right? I mean, if you got a pitcher and you want to know how much it holds, you're talking about the empty space in it, right? How much water would fit in it. Okay? We're not talking about that. We're talking about solid. We're talking about the volume of if we were going to make this thing out of plastic. Now, you do have some empty space through here, right? There's a hole through here, right? We're ignoring that, right? We don't want to count that as volume. The solid is this ring-like area, right? So let's make sure we understand what we're finding. So we're trying to find we're trying to find the volume of the kind of this blue solid mass. This empty space through the middle is not being counted. Okay, well, I go back to what we have work. Right? We need to identify what the slice is and find the area of that slice. Well, in this problem, when we reflect this, right, and again, not necessary that you draw this, but right, isn't this our picture? Like that? And what is a slice? Oops. Did that wrong. Isn't that the slice? Like that? What do we say we call that? A washer. This is a washer. Or a donut. Or a ring. I'm going to call it washer most of the time. Right? This stuff don't. Right? We're okay with that. I'll probably call it washer most of the time. Right? And that's what the books typically do. But you can see right down here it says disc/washer, right? So when you revolve and create a circular slice, if you've got some empty space in there, if there's some space between your region and your axis of revolution, you're going to create some empty space. You're going to have not a solid disc slice, circle slice. You're going to have a ring slice. What is the area of a ring? What is the area of a...
That's the area of the minus.
It's the area of the big circle minus the area of the little circle. Now, here's what we're going to do. We're going to call big R the outer radius, and we're going to call little r the inner radius, right? So we're going to have big R, and we're going to have little r. Because we've got two circles. We've got an outer circle and an inner circle. So here is the area formula we need for a washer. Now, we could factor out a pi and do big R squared minus little r squared, which is probably what we'll do. Okay? That's probably what we'll do, because then we can pull the pi out in front of the integral. Okay? So, back to our notes. We just found another type of slice. A washer. The area of a washer is pi times the quantity big R squared minus little r squared. And so we're talking about, and that could be horizontal or vertical, but big R and little r, right? A washer. So, if you have washer slices, according to the formula, we need to write in our integral the area of a washer. So that is this formula right here. So when we set up our integral, we have to identify big R and little r. Now, radius, here's the key. Radius always comes from where? Radius are always measured from center. Where's the center in this problem? The axis of revolution. The center is the axis of revolution. So here's what you got to have. You've got your strip. Here's this strip. Everybody look up here. So my marker is going to be this red strip I drew in. What I have happening is I got this marker, I got my strip, I got it revolving like this, right? Well, there's empty space, right? There's empty space. But where's the center measured from? The center's here, right? So as I revolve around, the axis of revolution, the center's that axis of revolution. So my marker does me no good. This strip here does me no good. Right? This strip, is that my radius? That's not my radius. It's big R minus little r, which is not what I want. I want big R squared minus little r squared, right? So what I have to do in a problem like this is I have to draw two other strips. I got to draw big R, and I don't have to draw it inside here, I have to draw it out here. Big R is going to go up to here Isn't that going to be big R? Big R is going to go from the center to the outer edge. And where's little r? Isn't little r always going to go to the x-axis? The little circle is going to be to the x-axis. So again, I don't have to draw all this stuff down here at the bottom. I don't need all this stuff. Okay? Matter of fact, we'll get to some problems here, and I'm not going to draw them. I'm just going to draw my strips. But I just want you to kind of see, as we revolve this, what's being created. Okay? So you understand that there's a wash. But I got my big R and my little r, so I'm going to write those down. I think it's really important to get in the habit of writing these down first and then putting them into your intervals. So what's big R? Top minus bottom. So what's this y value? Root x. Minus -2. What's little r? 0 minus -2. Now, clearly, I can simplify those a little bit, but I like, when I write them down, you're going to see me always write top minus bottom. You might have been wondering on these other problems why I kept writing -0, -0, -0, why they keep doing it. Because I'm reminding myself, it's top minus bottom, it's right minus left. So here I got top minus bottom, I got right minus left. So when I set up my integral, it's going to be pi. Don't forget the pi's out in front, right? We factored out the pi. And then it's big R squared minus little r squared. So it's big R squared, so square root of x plus 2 minus, and then I got my dx. And then the strips fill the space from where to where? 0 to 4. It still strips fill the space. Even though I'm not using this strip for anything, it's important that I understand it's still the strips fill the space. I mean, it's like the slices. The slices fill the space, you might say, from 0 to 4. It'll be the same thing. Okay, type that in your calculator. I think it's important to write the big R and the little r over here, and then remember, okay, now it's big R squared and it's little r squared, because remember, when we just have our circle slice, it's pi r squared, but that might be a top minus bottom, so it might be something subtracted, and then that's all squared. So sometimes we mix up, that. So understand what it is we're doing. Big R squared minus little r squared, when we have empty space, when it's a washing in there. Okay? All right. So let's take a look. You guys can just copy these problems down. Let's take a look at, let me see. I've got a couple of AP problems from earlier years. Okay, here we go. Right here. Let's do, this is from 2011. Okay? So, do part C right here. Do part C. Now, you guys, it says do not evaluate. You guys can evaluate it. I think that's because it was a no calculator one that year. Nah, it was probably a calculator one, but I think they didn't care. If you could set it up, they know you could type it in the calculator. So, but go ahead and calculate it. What?
Do I equal 0 the center? I don't know what the center is.
What do you mean the center?
Like, rotate, this is a washable one.
Uh-huh. It'd be empty space. The center's always what it's revolving around. If I take and I revolve around a certain axis, the center is where the axis of revolution is.
So then where's the second? Like, you're gonna draw.
Well, anytime you have a washer, right, and here's a center, one of the radius always goes to the outer edge of the region, and the little r goes to the inner edge.
So how do you know where the inner edge is?
Well, you draw it. I mean, just draw in your axis of revolution. Did you draw that already? Let me see.
No.
There's white.
Oh, I just.
There's white. Right, that's the white. Right. So you revolve this like that. So where's your outer? So you start at the center. So your radius starts at the center. Well, not there. It's got to go into the region. The region is just revolve. So put your pencil in there. And then where's the outer edge? Right at the outer edge. This is the region. That's the region. Draw from here to the outer edge. You get it. The inner edge. All right, if you're having trouble seeing this, let me show you here. I've got a picture of this. Okay, look at this. Let me see if this helps. Maybe you got it. That's fine. But everybody look up here for a second. Okay, so here's my region. Y equals 1 is my axis up here, right? Okay, so if we're going to revolve that around y equals 1, it's going to look something like that. So you have to imagine that. It's good to imagine that. Okay. Right? So it's important, I think, to think of it that way. Okay, so back to your problem. So Tim, you got something? You got an answer?
I have something here's going on.
Well, I don't care. You don't have to evaluate. Do you have an integral set up? I don't know. Something weird. What's going on with your cat? Weird. You had weird things going on with your cat crazy in the bed. What are you trying to do? Graph? We don't need to graph this one. They already give you the graph. What you need to do is draw. What you need to do is draw. Okay, you got an answer, Max?
Yeah.
Will, you got an answer?
You have the wrong curves.
You got what?
The 8x. The bottom one is the 8x. Yeah, it's top.
No, it's big R minus little r.
Big R squared.
Yeah, so it's 8x cubed squared minus sine of pi x squared.
Well, you got to do your strips. You got to write down big R and little. Okay, so let's talk about this. Okay, so here's our region. Right? Don't really need to shade it, but we're going to revolve this region. We all saw the picture. It's revolving up and around, right? So you're going to have these washers, right? You're going to have these washers like so, right? Now, region's actually down here. Let me redo that. Let me make it a little fatter so it's a little easier to see. So here's our axis of revolution coming right through there, right? Right there. Big R is going to go down here to our outer edge. So it's going to go from here down to there, right? Isn't that big R? Little r is going to go from the center to the inner edge of the region. This is the region. This is the shaded one, right? So it's going to go from here to here, right? So this one is big R. This one is little r. Okay? So Emily, when you said big R is going to be 8x cubed, the reason I said no is because big R is this strip. How do we find the length of a strip? Jesse, say it again. Top minus bottom, or right minus left. So big R is this strip right here. So what's the top Y value? What's the top Y value? 1. Minus, what's the bottom Y value? 8x cubed. What's little r? Emily, what's little r?
1 minus sine.
There we go. There we go. Now we're getting it. All right? Got to draw your picture. Got to think of your slice. Got to draw the radius. The radius has to come from the center. The center is the axis of revolution. You got to picture the slice if it's helpful, but this is big R, this is little r. Now, what do we set up for the integral? The area in here has to be the area, right? The area of the washer is pi times big R squared minus little r. See how there's too much to keep track of? That's why I think it's so important to write out big R, write out little r somewhere. Don't try to go right into your integral with it. Now, some people will get away with that. Some people can do that, and that's fine. I'm not going to penalize you if you don't write out big R and little r separately. But if you don't set up the right integral, that's most of the problem, right? So if on the quiz you can't set up the right integral, obviously the answer will be wrong, and you'll pretty much miss the whole problem, right? So getting the integral set up right is obviously the key. So big R, little r. Big R is a strip, little r is a strip. Strips we get by doing top minus bottom or right minus left. What did that come out as an answer? Anybody type it in yet? Oh yeah, and it's from what to what? The strips fill the space from that x coordinate right there, 0, 1. If they were horizontal strips, then it would go from 0 up to 1. These are vertical strips, and so they're going 0 to 1. I don't even know. I mean, I trust you, but because on the exam that year they didn't have to do it. Okay? But okay. There's our answer right there. Did they come out? They came out with that. 6 pi over 7.
My calculator.
Did that say 2 times 3 pi over 7? Oh, 2 minus 3 pi over 7. Anybody get that? Is that what yours said? 2 minus 3 pi over 7.
Mine gave me the decimal.
Oh, I gave it in a different form. Okay, let's try another one. Now, let's do one more of those, and then we got to talk about some other scenarios. Okay, so let's look at, let me see, is it 2013 I wanted to do? Oops. Stop it. Yes, let's do this one. Part B. I don't know, did I ever hand out any of these 2011? sounds like 2011, I didn't know. 14, 16, I think I paid that, right? 2014, 2016. Okay. Okay, part B. All right, so, right? Now, I know I keep showing you these revolutions, but you're not going to have access to these, obviously, when you do a problem, and I keep saying it's not important that you draw them or look at them, but I think it's good to just picture the thing revolving a little bit and kind of do that. So, you know, there's your big R, and there's your little r, right? But that would simply be, that would simply be, if we go back to the picture, okay? So if I'm doing this problem, I'm just saying, okay, y equals 4 is up here. This region is going to revolve up and around this, right? Put a little arrow here to show that. It's going to revolve up and around. So my big R is going to go to there, and my little r is going to go to there. I mean, that's just, you know, that's it. That's all you need. That's all you need. So what is big R?
4 minus 2x squared minus 6x squared.
That bottom one is, and you do have to be able to identify those, but you should be able to. Cosine, right? Cosine is going to start up and go down. A parabola like that. So you should be able to. And then that'd be in parentheses, right? Now, you can certainly simplify that. The 4s, I think, would cancel, but it's not important that you do. Little r would be, and actually you could just, if this was the AP test, right, and if this was actually a graph. Now, the problem is a lot of times, like on the quiz, I may say y equals this and y equals that, right? And then you can't do as much. But if you define them, or they've been defined as f and g, you could just do 4 minus f of x, right? On the AP test, that's fine. And here you can do 4 minus g of x. But I'll just go ahead and write it out. Okay, so there you go. And then your integral is 4 minus f of x all squared. I'll shortcut that a little bit, but obviously you type it in. Minus 4 minus g of x all squared, dx, don't forget the dx, from 0 to 2. So these have all been vertical strips, and don't forget the pi out in front, right? Easy to forget that as well. So you got pi, then you got big R squared minus little r squared. All right, now read number, and then what did that come out? Did you get an answer? It doesn't matter, right? Whatever. I assume we can type it in right, but it will matter in the quiz. You've got to get a right answer. Okay, now here it said do not evaluate. So a lot of times they do that because they just don't care. They just want you to set it up. Okay, I don't remember if this was a calculator one. This is probably a no calculator one, actually. Because you can do antiderivatives, all this stuff. They did have you do an area here, so you can. All right, so now let's look at C. Everybody read C. We're reading letter C here on this one. Okay? Right. Okay? So, now we got a different scenario. Notice this is not a revolved solid or a rotating solid. So, you're going to have one type of volume problem where they're going to say, find the volume of the solid that is created when you revolve or rotate a region. Well, anytime you revolve or rotate, you're going to get a circle, right? Now, you're either going to get a solid circle or you're going to get empty space, so you have a washer, right? So you're going to get a circle slice or a washer slice when you revolve. The other type of problem you're going to get is like this, where they give you a region and it is the base of the solid. So think of the region as being flat on your desk, and up off of your desk is going to come the solid. Okay, now, again, I've got a nice picture of this, and when you can see them a little bit, it's helpful. So we're going to take this region, we're going to lay it down and kind of try to see it three-dimensionally. So that region is being laid like that, and then squares are coming up off of that base. But they still, so in other words, it's still a matter of, can everybody see that? So what is the strip now when you look at it up here? Well, right, strip is top minus bottom, but what part of the slice is the strip? Well, first of all, what shape is the slice? It's a square. They told you that. They told you the cross sections are squares. Where's the strip up here? It's that black line right there. Right? So coming up off of here, we have squares. That's what's going on. Okay? So you can see what it is creating here. Now, again, not important that you can easily see this. Stop it right there. So this is creating a solid, but let's focus on this right here. Let's focus on this picture. So when you're working this problem, it says, okay, this region is the base of a solid. So you think to yourself, okay, that's flat on the ground, and the cross sections, and it says taken perpendicular to the x-axis. So they tell you they're vertical. If it's perpendicular to the y-axis, they'd be horizontal. Perpendicular to the x-axis means they're vertical strips. So you draw in a strip and you say, okay, coming up off of this base are squares. So here I got a strip, and boom, 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 coming off of here are squares. See what I mean? So over here they'd be little squares, right? Over here they were little squares, like this one right here, right? Because there's your strip. There's your strip right there. The strip is the side of a square. What would we call it? Would we call it R? We're going to call it S, right? For a side of a square. What's the area of a square? What's the area of a square? S squared, right? One side squared. So in our formula, in our notes, right, let's add another type of slice. Another type of slice could be a square. We could have square slices. The area of a square is S squared. So we could have square type slices. If I want to make it a little bit three-dimensional, I could, whatever. Right? We could have square slices. But here's going to be your strip right here. Here's going to be your strip. All right? So, if we go back, well, let's go back to that picture. Okay? So we're imagining that. Now, I've got some other pictures of these things that I could, oh, no, not any that I, well, yeah, I do too. Let me go back to here. Show you another one with squares. Right here. Here's a region. It's a circular region, different region. Okay? This time we're going to do perpendicular to the x-axis again, so vertical. Here would be some slices. Right? We can kind of see that as I rotate it through when we look at it two-dimensionally, three-dimensionally, but think of it laying flat. Okay? Here would be the solid that would be created, very similar to the one we're talking about. Here's your strip right here. Here's your strip. It's one side of the square. We're going to do top minus bottom. We do top minus bottom to get that. Okay, there's your solid. Okay, or we can just see each square and the integrals, adding those up. Okay, so that's what we got going on. All right, now let's go back to that. So what would this look like? So we would come in here and we'd still have our strip drawn in. Here's our strip. Coming up off of this are squares, right? So it says region R is the base of a solid. For this solid, each cross section, meaning slice, perpendicular to the x-axis, so that's why I know it's vertical, is a square. Okay, so I put in my strip. Coming up off of here are squares. Coming up off the page are squares. Okay, this strip is one side of the square. So I'm going to call it S. And what is the S? Now this is different than what we did before, right? We were doing R, we had big R, we had little r, we had two strips. But now this strip is actually what I want. Okay, what is that strip? Top is what? G of x. I'm going to write it out. 4 cosine 1/4 pi x minus parentheses 2x squared minus 6x plus 4, which is how you have to type in your calculator, right? And what is my integral that I set up? 0 to 2. Now, if this was the AP test, and I had called this S, or better yet, S of x, then I would just put S of x squared dx. I would just do that if it was the AP test. I think on our quiz, I think you ought to write that out. But you're going to type in your calculator that way, but maybe identify it. Actually, on our quiz, I don't care. If you identify that as S of x squared, right, and do that. But I want to see it. Probably should write it out. Probably should write it. At some point, you need to make sure you have parentheses in the right place. But again, if on your calculator you define, to be honest, I think that takes more time probably in this problem. But you can define this as f of x, you can define this as g of x, then you can define s of x as that minus that. But if by the time you type all that in, you'd be better off just typing it out. So, okay. Now, what about pi? Do we throw pi in there? No, this is area of a square. So it's one side. This is one side of the square, just like we saw in that picture. Okay? So what other kind of slices could we have? Notice in our notes we got room for a couple more. Okay? Well, sometimes we do This is isosceles right triangles. Now, why do we do isosceles right triangles? Well, because, well, no, I'm not going to do isosceles right triangles. All those are easy enough. And sometimes they show up in the p-test, but not us. We're going to do equilateral triangles. So, now imagine coming up off the page, and you can think about it, right? Picture here, coming up off of this are equilateral triangles. Like that, right? So what is the strip? But aren't they all the same, right? Now what's the area? What's the area of an equilateral triangle? What's the area of any triangle? Problem is we got two variables here. Okay, now you said that's your base. Okay, that's fine. If you want to call that B for base, that's fine. We can call that B for base. Here'd be your height, right? Well, I want to get rid of that height. Now, what type of angle is this in an equilateral triangle? That's 60. So what's this one up here? 30. Aha, 30-60 triangle. So wouldn't this... So if this is my base here, this would be 1/2 B, right? Well, you guys remember from trig, if this is 1/2 B on a 30-60, if it's 1/2 B across from 30, what is it over here?
2 square root.
Let's just do this. 30-60. If this is 1/2, what's this? 1. And what's this? Root 3 over 2. It's a unit circle, right? Unit circle. If the hypotenuse is 1, then across from 30 is 1/2, and across from 60 is square root of 3 over 2. So if this is 1/2 B, what's the hypotenuse? This is 1/2 B, what's this? 1B. And what's this? Root 3 over 2B, right? They're in the same ratio. So if this is 1/2 B, this would be B, and H here would be root 3 over 2B. So what is the area of this triangle? 1/2. What's my base? B, right? And what's my height? Root 3 over 2B. So multiply that all together, what do you get? And isn't B my strip? B is the strip, right? So it's 1 root 3 over 4 B squared. So back to our notes. So another type of slice is an equilateral triangle. The area of an equilateral triangle is root 3 over 4 B squared. So and there's your strip right there, which is your base. Okay, and the last one, we can have other kinds of strips. We can have all kinds of, or slices. We have all kinds of slices. These are the slices I'm going to want you to be responsible for.
Is your base on that just top minus bottom?
Well, it's a strip, yeah. And the strip is always top minus bottom or right minus left. So it depends if it's horizontal or vertical, right? Okay, and the last one would be, here's a different base, but that different region, doesn't matter. And here we got horizontal, so that doesn't matter either. But the last one would be semicircle slices. Semicircle slices is the last one we would have. Okay, now, what part of your first of all, what's the area of a semicircle? 1/2 pi r squared, right? Now, here's my strip right here. What part of the semicircle is that? It's the diameter. Aha, diameter's not in here. Now, you could do your strip and cut it in half, which means you'd have to divide it by 2 and make it a radius and then put it in, but that gets confusing because you forget the 1/2, then you got this 1/2, then you got to cut it in half. Let's change this formula for our semicircle to have D in it instead of R. Because every time we do a semicircle slice, the strip is going to be the diameter. So let's change our equation. So what is R equivalent to when it comes to diameter? 1/2 D, right? right? So I'm going to replace R here with 1/2 D. Now let's rearrange that. So what does that become? 1/8, right? Because you square this, will be 1/4 times 1/2. So 1/8 pi D squared. That's the one we're going to memorize. Okay? Now you can do this. I don't care, but I would advise against it. I think I would just memorize this. Okay? So, in our notes, the other type of slice we could have is going to be a semicircle slice. And the equation, or the area of a semicircle slice is 1/8 pi D squared. Okay, and there's your strip right there, which is your diameter. So, your strip is the D in this one, your strip is the B in this one, your strip is the S in this one, your strips are the big R and little r in this one, your strip is the R in that one. You got those equations, you imagine those slices, you plug those in, you put those into your integral, you got it, and of course everything comes back to this right here, where we're adding up these pieces of volume. We're adding up the slice times its thickness, which is volume, the integral adds that up. Okay? Alright, so, let's alright, so in your LH, see the next line down here says 13, 15, 22, 25, this is page 419 still, 38, 39, okay, now there's asterisk by a couple of those, which I don't even know why. 13 had multiple parts, so I don't, because what they do is they take the same region, they revolve it around different things, okay, so that's page 419, and then on that next one there, let's do 49, let's just do that first one. So on page 421, let's do 49 ABC.